Let's have a look at this definite integral. So integral from 0 to 2 of sine of x squared dx. So there's not really anything obvious to try here. There's no nice trig identities with a squared inside. I guess we could maybe try a u substitution where u is x squared, but this seems unlikely to do us much good just because there's nothing outside of the sine function to work with, right? Normally, to do this sort of substitution, we would expect to have an x on the outside of the function, so that we could make du out of that x, right? We could maybe try to push a little harder on this idea by also moving the x to the other side here. So 1 over 2x du equals dx. And x is, right, on our first substitution equation here, x is really the square root of u. We do have to be kind of careful because of the plus or minus here, but for these x values, x is always positive, so we always choose the positive square root. So we could replace this x down here with the square root of u, and that would give us 1 over 2 square root u du equals dx. And so now we could write out our substitution. So integral, let's see, when x is 0, u is 0, and when x is 2, u is 4. So this is going to be sine of u times dx, which is 1 over 2 square root u dx, du, sorry. So this substitution, it worked in that we turned all the x's into u's, but now we have to figure out how to evaluate our new integral. And this new integral doesn't look any more doable than the old integral. I mean, there are things to try. I guess we could try integration by parts, but it turns out that no matter what you try with this definite integral, you won't be able to find a formula for an antiderivative of this function. So we're kind of stuck, right? We're kind of stuck because our usual tool for evaluating definite integrals, which is the fundamental theorem of calculus, our usual tool doesn't do us any good just because we can't find an antiderivative. So what can we do to get some handle on this definite integral? Well, we're going to have to go back to our original meaning of what a definite integral is calculating. Remember, a definite integral from 0 to 2, it's the signed area between the graph and the x-axis. So it's this blue area minus this red area, right? And so, right, because we can't use the fundamental theorem of calculus, we can't evaluate this integral exactly. The best we can do is approximating it. And to approximate it, well, we could, back in the day when we first talked about definite integrals, we approximated areas using rectangles. So we could use exactly the same idea. Right? If we decide how many rectangles we want to use, maybe 4 rectangles. Let's use n for the number of rectangles. So if we use 4 rectangles, that means we're going to break the interval from 0 to 2 into 4 pieces. So like this. And on each piece, we put a rectangle, and we have to decide how we choose the height of that rectangle. So there are 3 main choices for how to choose the height of the rectangles in this kind of situation. So again, we're going to have n equals 4 rectangles, breaking up our intervals like this. So if you use left-hand endpoints, then that's going to look like this. So at each interval, you use the left-hand endpoint of that interval, the height of the function there, to decide how tall your rectangle is. So on this first interval, the left-hand endpoint has height 0, and so the rectangle has height 0. On the second interval, the height is up here, and so our rectangle is that high. On the third interval, our left-hand endpoint is 1. The height of the function at 1 is up here. And so our rectangle looks like that. And then on the fourth interval, the left-hand endpoint is 1.5, and so our rectangle looks like this. Of course, if we wanted a good approximation, we would use many more rectangles than just 4, but right, this is just for illustration. So if we name these data points, or these x values that we used, x0, x1, x2, x3, and x4, notice that we're starting at 0 and we're going up to, there are always n x values. So for left-hand endpoints, right, what we get is each of these has some width, which we'll call delta x. So for left-hand endpoints, the total area is, the width is, let's see, for the first rectangle, it's the width, which is delta x, times the height, which is the function at the left-hand endpoint, so x sub 0, plus, for the second rectangle, it's the width, which is still delta x, times the function at the next x value, x sub 1, and so on, all the way up to, the last rectangle is going to be delta x, which is the width, times f of, well, we have to be careful. For the last rectangle, the left-hand endpoint is the second to last x value. So this is going to be x sub n minus 1. Of course, all these terms have a delta x, so we should probably factor out that delta x. So delta x times f of x sub 0 plus f of x sub 1, and so on, all the way to up to f of x sub n minus 1. Okay. So for this particular example, right, it's calculator time. We can punch everything into a calculator and see what sort of mess we get. So let me make sure I'm in radian mode. Yes. So delta x here, right, our interval is from 1 to 2. So this is length 2, but we're breaking it into 4 pieces. So delta x is a half. Okay, and then f of x sub 0. So x sub 0 is 0, and sine of 0. F is my name for the integrand function. So in this example, it's sine x squared. So sine of 0 squared is 0, plus, so this is the term 0. I'm not dividing by 0. I'm just labeling what term we're on, what x value we used. For this next one, for the next term, the x value is the first is x sub 1, which is a half. So sine of 1/2 squared plus, and then our next x value, sine of 1 squared plus, and then our next to last x value, sine of 3/2 squared. And then we can do all this arithmetic, right? At this point, since we've already accepted that we're only approximating the integral, right? What we're getting is an approximation for this integral. We're okay with punching these values into a calculator for sine, because it's true the calculator will only give us a decimal approximation, but we're already approximating, so a decimal approximation is fine. So let's see. So sine of 0.5 squared, so sine of that, plus sine of 1 plus sine of 3/2 squared, and then all divided by 2 because of the 1/2 out front. So I get 0.9335 approximately. Okay, well that's using left-hand endpoints. Of course, we didn't need to use left-hand endpoints. Another fine way to do it is for each interval, instead of choosing the endpoint at the left, choose the endpoint at the right. So for our first interval, that's this spot, and so our rectangle is this blue rectangle. For the next interval, the right-hand endpoint is at 1, and so the height of the function is way up here, so our next rectangle is that tall. For the next interval, the right-hand endpoint is at 1.5, and so our rectangle is like this. And then for the last rectangle, our right-hand endpoint is at 2. The function is all the way down here if it's negative, and so our rectangle is negative like this. Okay. Now we can work out a similar expression for right-hand endpoints. So for right-hand endpoints, we get, again, the width of each rectangle is delta x. The only difference this time is which x values we're using. The height for the first rectangle, instead of being the function at x sub 0, well, now it's the function at x sub 1. So f of x sub 1, and so on, up to the last one. And for the last rectangle, we used the last x value, so f of x sub n. All right, so this is for right-hand endpoints. For this particular example, this is going to be 1/2 times sine of 1/2 squared plus sine of 1 squared plus sine of 3/2 squared plus sine of 2 squared. Okay, and then dump it all into a calculator. Let's see, 1/2 squared is 1/4, sine of that, plus sine of 1, plus 1.5 squared, sine of that, plus sine of 4, all divided by 2. And for this, I get 0.5551, approximately. Okay, so this is using right-hand endpoints and left-hand endpoints. Some people, for left-hand endpoints, they call this L sub 4. The subscript 4 is because we used 4 rectangles. So this is, I guess this is L sub n, since the formula I have written down is using n rectangles. And then for right-hand endpoints, often, well, some people like to call this R sub n. R for right-hand endpoints, and n because we used n rectangles. Okay, well, if you look at this diagram, it seems a little bit silly to use right-hand endpoints or left-hand endpoints, because you're sort of, whether you use right-hand endpoints or left-hand endpoints, there's always a big corner that's sticking out, right? Either it's an extra corner that's above the graph, or a missing corner that you should have gotten below the graph. And one nice way to compensate for these extra and missing rectangles is, instead of using the endpoints of an interval, use the midpoint of an interval, like this. So for this first interval, the midpoint is right in the middle here, and so the height of our rectangle is there. So like this. Let me erase all of my rectangles and just start over. It's hard to see what I'm drawing. Okay, so for our intervals are like this. For our first interval from 0 to 0.5, we're using this x value right in the middle, and so the height of the function there is here, and so there's our first rectangle. For the second interval, the midpoint is there, the function is up here, and so our rectangle looks like this. For the third interval, our midpoint is here at 1.25, I guess. The function is up there, and so our rectangle looks like this. And then for the last interval, our midpoint is here, the function is there, and the rectangle looks like this. Now, even without doing any calculation, you can tell that this is going to be, it looks like it's going to be a lot more accurate. We still have extra rectangles, or extra little triangles, and missing little triangles. But for each rectangle that we drew, well, for most of the rectangles that we drew, there is an extra triangle and a missing triangle, and those will sort of balance each other out at least a little bit. So for this reason, midpoints usually give you a better approximation than using left or right hand endpoints. There is one exception for this particular example, which is in this one in the middle, this third rectangle, we actually have two little extra triangles instead of one extra and one missing. But that doesn't usually happen. Okay, so for midpoints, we would call this m sub n. The width of each rectangle is still delta x, but the tricky thing about using midpoints is we can't use the same x values as we had before, right? The x values label the endpoints of these intervals, but we didn't use the endpoints of the intervals. We used the midpoints. So for this first term here, the x value we need is the midpoint between x sub 0 and x sub 1. And that's the average. So x sub 0 plus x sub 1 over 2. And then for the next one, it's f of, the midpoint for the next interval is x sub 1 plus x sub 2 over 2, and so on. And then for the last rectangle, it's f of x sub n minus 1 plus x sub n over 2. Okay. So let's see, for our particular example with where the function we're talking about is sine of x squared, let's go ahead and write down what this gives us. So this is midpoint with 4 rectangles. Delta x was a half. So sine of, the first interval is from 0 to 0.5, and so the midpoint is a quarter. So that's squared, plus sine of, so the midpoint here is 3/4. Right, this is from a half to 1, so the midpoint is 3/4, squared, plus sine of, and the midpoint for the next interval, well, the next interval is from 1 to 3/2, and so the midpoint is going to be 5/4 squared. And then the last one is the interval from 3/2 to 2, and that midpoint is 7/4 squared. All right, and now it's calculator time. Now we just dump everything into a calculator. So 0.25 squared, take sine of that, plus 0.75 squared, take sine of that, plus 1.25 squared, take sine of that, plus 1.75 squared, take sine of that, and then divide the whole thing by 2. And we get 0.8373, 4. Okay. It's kind of reassuring that this midpoint approximation came out between the right hand and left hand endpoints. That's pretty typical. So you might be thinking, why ever use left hand or right hand endpoints? Why not always use midpoints? Well, the main disadvantage to using midpoints is the fact that you have to evaluate the function at these different x values, right? So how these integral approximations usually get used out in the wild, in the so-called real world, is you have some function that you are working with, right? Something like this, but you don't actually know the graph, and you don't have a formula for it. It's just some function that you have in the abstract, like, say, the population of a certain city or the temperature of a certain location. These are things that you don't have a formula for. If you want to evaluate that function, you actually have to go out into the world and gather data. And if you gather data, you don't always get to choose what x values you gather data for. If your horizontal axis is time, you can't really choose, once you've gone out and gathered data, you can't after the fact, change the time at which you gathered that data in the past. You can't go into the past to change the time when you gathered the data. So if you have a collection of data that you have already gathered, you're stuck with those data points. And in particular, you're stuck with the x values that are in your data set. And so you don't get to choose the x values. In particular, in that situation, if you're working with a given data set, you can't use midpoints because you don't know the function at the midpoints. You only know the functions at your data points, which are typically at your endpoints. So the main drawback of midpoints is if you're dealing with data out from the world, you can't use midpoints typically. But if you can use midpoints, then you do use midpoints because using midpoints is more accurate.